Hello everybody, welcome back to another video, and in this video we'll be looking at a useful integral, and that is the general form of the inverse tangent integral. So we know that the integral of 1 over 1 plus x squared dx is equal to the inverse tangent of x, which is the input. So, but what would happen is if we had 1 over a squared plus x squared instead? Well, we have some random constant, so what do? Well, the first thing we can see is that we have some constant plus x squared. So the first thing that we can see is that we can use a trig substitution. So that is the first method that we'll be using. So we'll first be looking at a trig substitution. So what we'll do is, since we have something plus x squared, we'll set our x to be a tangent theta, because we know that if we have something plus x squared, we are going to need to have a tangent there, and because we have a squared, we want to set x to a, because eventually we're going to need to square the x. So that means that taking dx on both sides, you'll get a, and then you'll get secant squared theta, but because of the chain rule, you have to multiply by d theta, because theta is a function of x. So now let's substitute these into our integral. So we have 1 over, and then we have a squared plus, and then x now is a tan theta, and we're squaring that, so we can just square both terms. So we have a squared tangent squared theta, and then our dx now is a secant squared theta d theta. So we're in the theta world right now. And the first thing that we notice here is that we can factorize the a squared on the denominator. So we have 1 over a squared, and then we have 1 plus tangent squared theta, which is why we use a trig sub, because we know that 1 plus tangent squared theta is our trig identity. So first of all, now our dx, we can take the a out because it's a constant, and now we have secant squared theta d theta. And using the identity that 1 plus tangent squared theta is equal to secant squared theta, well, we can use that exactly right here. So we now have a times the integral of 1 over a squared times secant squared theta, and then secant squared theta d theta. Now, first of all, this is the same thing as writing 1 over a squared times 1 over secant squared. So we can actually take out the 1 over a squared once again, because it is simply a constant. So we know that this is going to be a times 1 over a squared now. Now times the integral, we still have the 1 over secant squared theta, and now our dx is secant squared theta d theta. So we can see that very, very nicely, this secant squared theta and this secant squared theta cancel exactly. So we're just left with 1 in the integral, and this a is to the power of 1, so this would cancel, and you would be left with 1 over a times the integral of 1 in the theta world. So this, of course, would produce 1 over a times theta. However, what is theta? We need to get back to the x world. So we know that a tangent theta is equal to x. So to isolate tangent theta, we have to divide by a on both sides. So what we need to do is we need to divide by a. So what happens now is we actually get tangent theta is equal to x over a. And now we want to find theta. And how do we find theta? Well, we know that if we take the inverse tangent of the tangent, by definition, that should just give us the input. So if we're taking the inverse tangent of the tangent of theta, we should just get theta back. So let's take the inverse tangent on both sides, like so. And we can see that this and this cancel, and we're just left with theta is equal to the inverse tangent of x over a. So now, replacing our theta with that, we get the integral of 1 over a squared plus x squared dx being equal to 1 over a, and our theta is now the inverse tangent of x over a. And then we can put the plus c now, and this is our answer. Now let's look at the second method, which is an arguably much faster method of looking at it, but it would be quite hard to spot if you didn't know the step. But it is certainly doable, and that is using a u substitution. So the second method that we'll be looking at is a u substitution. So we have the integral, just a reminder, of 1 over a squared plus x squared dx. So what we can actually do is we can factor out the a squared immediately, 1 over a squared. So this is actually equal to the integral of, and now let's say we factor out the a squared. We have a squared now factored out. So what are we going to have in this bracket? Well, we're going to have 1, because a squared times 1 is a squared. And then what times x squared produces a squared? Well, or sorry, what? Yeah. So then that is x squared over a squared. So we need to have x squared over a squared. It should be what multiplied by a squared gives you x squared, because that is what you're trying to find. And you can see that by just dividing on a squared by both sides. So we get this in our denominator like so. And now, something that we can see here is that we can factor out this 1 over a squared. We can take this out of the integral because it's just a constant like we did in the trig substitution. So we now have 1 over a squared times the integral. And we know that if we have a squared over b squared, this is equal to a over b squared. And a over b entirely in a bracket squared. And this is useful in going both ways. Like either way, this will be useful, a useful identity. So now we have the integral of 1 over 1 plus x over a entirely squared. And I apologize for the bad handwriting. I'll just rewrite this again. You have x over a entirely squared. And you have the dx. So now what we see is that we have 1 plus something squared. And that looks like a good case to use a u sub, because we know that 1 over 1 plus x squared is the arctan integral. So if we set u to be x over a, we know that du is going to be it's just going to be 1 over a, and then therefore dx is going to be a du. So now we can actually take this a out immediately. So we have a times 1 over a squared times the integral of 1 over 1 plus u, because u is x over a squared still, and then that was our dx. Our dx was a du, which we've taken the a out here. Now we have the du. So now we're just integrating 1 over 1 plus u squared in the u world, which is the inverse tangent of u. The inverse tangent of u, that is an important fact. And we can see that we can cancel this a, and we get 1 over a times the inverse tangent of u. But what is u? U is x over a. So now, substituting u to get back into the x world, we get the integral of 1 over a squared plus x squared dx being equal to 1 over a times the inverse tangent of u now, which is x over a. And we can put the plus c, and we are done. So thank you for watching.